Good morning, everybody. Everybody, come on, Bob. Well, welcome to the neuroprosthesis seminar for the month of November. I'd like to start off with an announcement or two. First of all, December 10th, Friday, December 10th, will be the last seminar of this calendar year. So mark it down, and the speaker will be Heidi Martin from the Department of Chemical Engineering. So an internal speaker. So please come on December 10th. She'll be talking about conductive diamond for implantable neurological devices. I have another announcement, and that is many of you have probably heard that the APT Center is losing our Director of Operations, Susanna Ivalic, who has nagged many of you in the room, I'm sure. She's taking a job at VA Central Office, so we'll have a friend in high places. But if anybody knows of anybody with an MBA or management experience who can keep cats like us in line, please encourage them to send a resume. We'll be advertising soon. Okay, with that, it's my pleasure to announce our speaker for today, Dr. Michael Goldfarb from Vanderbilt University. Michael got his undergraduate degree at the University of Arizona. Actually found out last night, spent some time volunteering in a prosthetics fabrication shop as an undergrad or in summers. Went on to graduate school at MIT, where he got his master's and doctorate in mechanical engineering and worked with a good friend of many of ours, Will Durfee, on hybrid systems, and actually wrote some seminal papers in the 90s that we still teach in class. So our BME students who you'll meet with lunch will have some questions. You'll have to drag up through the dust and the cobwebs. Your dissertation follows you everywhere you go. Just remember that. It's impossible to pick up an issue of the IEEE transactions on mechatronics and not see an article by Michael. And he's also won a number of Best Paper Awards from the International Society for Rehabilitation Robotics. Is that it? So I'm looking forward to some unique perspectives on advances in prosthetic design, and without any further delay, I'd like to introduce Michael Goldfarb.
Okay, yeah, thank you very much, Ron. Can everybody hear me okay? Yeah. First, let me say it's a real pleasure to come and give the talk, and it's just a delight for me to be able to visit and see all the great activity going on here. I also like to set up with the food up front, so I can just, pardon me if I occasionally get a muffin during my talk. Okay. Let's see. So yeah, let me get my laser pointer. Yes, so I'm going to talk about work that we're doing in my group in both upper and lower extremity prosthetics, and I'm going to spend maybe the 2/3 of the talk talking first about some work we're doing in a powered transfemoral prosthesis, so lower extremity, and then the last third or so talking about work we're doing in the development of a what we call a multi-grasp hand, or a dexterous upper extremity prosthesis. So I will start with in both sections. I'll start with describing the commercial state of the art. And the commercial state of the art in a lower extremity or in a transfemoral prosthesis looks something like this, where you have this suction socket that holds the prosthesis onto your residual limb. This is a knee joint, in this case a damper. Well, they're essentially all dampers. This is a modulated damper. This is Autobox C-leg. So it has a microprocessor inside that can make it damp more or less, depending on what you're doing. And then the foot-ankle complex is essentially a leaf spring. In all cases, these prostheses are passive, which means they can't contribute net power to gait. And because of that, amputees require considerably more energy when walking. This is 60% more energy, essentially, just in level walking. They walk more slowly. This is maybe something that's more evident. The fact that they can't contribute net power to gait means they would have difficulty stair and slope ascent. So in stairs, people will, assuming they're a unilateral amputee, will lead with their sound leg and then will essentially drag the passive or prosthetic leg up behind them. What's less obvious is that they also have difficulty in stair and slope descent. Now that doesn't necessarily require contributing net power to gait, but it does require the ability to adapt its behavior to a different activity. So level walking is one thing, and these are pretty good at level walking, but what we do in general in locomoting throughout a day involves a large variety of activities, and these legs the kinematics and the kinetics of going down slopes, downstairs is different than level walking, and it's important to get that right because gravity usually wants to accelerate you going downstairs and down slopes, and that's not a real stable way to walk. And so, in part because of the inability to adapt to the different terrain, amputees fall a lot more than lower extremity amputees fall a lot more than healthy subjects. In fact, they fall at essentially the same rate as institution living elderly, and they seek medical attention also at the same rate as institution living elderly. And this problem is worse in younger amputees than in older amputees, presumably because in younger amputees they're less inhibited by what they do. Now recently, and by that I mean within the past, I'd say 3 to 5 years, the robotics technology has become good enough so that you can start to put power in a leg, and in particular, I mean enough power and torque at the knee and the ankle to be biomechanically useful without having a device that's unwieldy or just too heavy to be used by an amputee. These advances have to do with much improved power density in motors, much improved energy density and power density in batteries, and much greater capability in microelectronics. And when you have power in the leg, you can do 2 important things. You can contribute net power to gait, again, going upstairs, up slopes, things like that, do essentially what the native limb does. But also, very importantly, you have the ability to adapt its behavior to various terrain and various circumstances. Because this has been enabled, one can see in the field a few emerging powered prostheses. This is the Eyewalk prosthesis from MIT/Hugh-Herr, which is a powered transtibial prosthesis, essentially a powered ankle. This is from Tom Sugar, another powered ankle. This is a powered knee, originally developed at a small startup called Vigthom, and then licensed to OSER. So my group, since I guess roughly 2004, 2005 timeframe, has been developing a powered knee and ankle joint. So we're at this point the only ones doing that, I guess, that have 2 powered joints in the leg. This is actuated by a pair of electric motors. Let's see, one is here for the knee, and then one is here for the ankle. It uses ball screw transmissions. So here's the knee joint, here's the ankle joint, and there's a battery embedded inside the structure here, which is, as it says, 30 volts, 120 watt hours. I'll talk more about what that exactly means in terms of how many steps you can take later. It has lots of sensors, which we need for control. It measures joint angles and joint angular velocities. It measures torque at the joints. It measures the load on the ball of the foot and the load on the heel, and measures the torque being imposed between, this is where the socket would be connected, so between the socket and the leg. Oh, and then also has 3-axis accelerometers on both the shank and the foot. We have, if you take this case off, there's a electronics board that has kind of at its heart this 80 megahertz 32-bit microprocessor, which I talked about advances in microelectronics before. This microprocessor consumes 400 milliwatts when it's kind of at full power. The computational power is similar to something like a 486 was, maybe a little bit better. But the difference is the 486, for those of you old enough to have had one, it had heat sink on the processor, and it had 3 fans, fan right on it, and usually 1 or 2 fans blowing across it. If you took those off and put your finger on it, and it'd burn your finger in a second or two. So that was taking probably 3 orders of magnitude more power. And so there have been several advances in microelectronics that enable these kinds of things, but this is certainly one of them. The total mass of this, and actually kind of as shown, but with the addition of a foot shell, which goes on the bottom, is 4.2 kilograms. That's set up for this particular subject, who's about 6 foot 2 inches tall. His daily use prosthesis is between 3.2 and 3.6 kilograms. The way he uses it is with the cover, which is 3.6 kilograms. So this is about 15% heavier than the passive prosthesis. The passive prosthesis he uses is a C-leg with something called a Freedom Renegade foot. So we're 15% heavier, which isn't bad, especially considering the fact that this can move itself as opposed to just being moved by the user. So one of the things that changes, when you do both this, and then I'll talk later as far as the upper extremity too. One of the things that changes when you change the capability of the prosthesis is the control. And in particular, having power in here changes this control problem a lot. With the passive prostheses, fundamentally, they can fundamentally physically only react. So a passive prosthesis is not going to move unless I take my hip and shake it around and make it move. A powered prosthesis, however, like this, can both act and react. So it can decide to do what it wants to do regardless of what I'm doing, and that is potentially dangerous, right? If I'm standing here trying to give a presentation and it suddenly thinks that I want to start running, then it can start running, and I don't have explicit control over that. So this is attached. It's a powerful 2-degree freedom robot, rigidly, to the extent that a socket interface is rigid, rigidly attached to the user, but without any explicit means of communication. So all the communication, at least in the way that we do this, is implicit. And so one of the ways I look at this is having power. I mentioned, the things you can do with power. You can emulate better healthy biomechanical gait in walking, slope ascent, stair descent, and so on. So you have this greater capability, but also you certainly have a greater liability. So if you do things wrong, you make it much worse than things would have been with a passive prosthesis. So I did mention this device that Vixon was making. So what they do is pre-program trajectories. And then you do this, you step on your heel a few times to give it a signal to change its behavior, let's say from level walking to stair descent. We don't really think that's a good way to go for various reasons, and I won't go into those now, but I can talk about them later if somebody has a question about it. This is the way that we do the control, and so this is a method that seems to be working pretty well for us. So I'll briefly explain it. What we do is segment the walking cycle. So this is just for level walking from heel strike to heel strike. This shows, by the way, this is the knee angle. This is all knee, this is all ankle. So this is knee angle, angular velocity, and torque as a function of stride. And we segment the stride into 5 segments, but it doesn't matter exactly how many you segment. But within each segment, each joint, we give it a real simple behavior, which is just a spring and a damper, which are passive behaviors. And people generally like interacting with passive things for multiple reasons. But within each of these, we measure the angle, we measure the angular velocity, and these others, the stiffness, the damping, and the set point are all parameters. And so this has this nice properties of being inherently passive, inherently stable. If I ever, at any time, I stop exciting the leg, if I stop giving imposing input onto the leg, it is guaranteed to just stop moving, which is a nice behavior. The other nice behavior about this is if you take this, again, blue measured normal behavior of the knee angle and swing and the knee angular velocity, and use these 5 of these functions segmented like this, then you get this red dashed line. So the blue is what you measure in healthy biomechanical gait. The red dashed line is what's reconstructed from this. So you can actually do a good job of reconstructing what the muscles and joints do by having a series of passive functions. And so you take that series of passive functions, and this is a state-based controller, and in each of these states, the knee and the ankle each behave like slightly different spring and damper couples, and then the user gives these natural cues to switch to the next one. And so, for instance, if I want push off of my ankle, the cue is that the angle of my ankle has dorsiflexed a certain amount. And once it's dorsiflexed a certain amount, that gives a cue. What that means to the system is that my center of mass of the body is sufficiently over that foot, so it wants to push off. And it pushes off by essentially just giving the ankle a new, the ankle spring a new set point. And what this does is several things. One is, if you have a position-controlled leg, then you have a high output impedance, and the person essentially rides on top of that leg. The person has no control of that motion. But the way we interact with our limbs have low impedances, and it's a real interaction. It's not just a reaction. So I don't ride on top of my legs. My legs are moving, but I can influence. The resulting motion is a combination of what the leg's doing and what the rest of my body's doing. And what this does is provide that same kind of matched impedance. Also, like I said, is if I just stop exciting my leg, if I don't roll my center of mass over to get push off, and if I just don't do anything with my leg, it's going to remain passive. So the only way it releases power is from me giving it cues. So the power, even though it's implicit communication, the power release is a direct result of what cues that I'm giving it. So at any rate, this approach seems to work well. You can kind of see it better. Oh, actually, I'll quickly say, you do have to parameterize it. So you have to give the joints their stiffness, damping, and equilibrium point at each state. This turns out, as far as we can tell right now, not to change too much from person to person, which is a good thing as far as parameterizing it. These parameters that I have in gray slightly change as you increase or decrease your speed. And so we set them up for 3 different speeds like this. These are the ones in gray are the only ones that change. And they change monotonically, so we could apply a function to those, but we don't have enough subjects to have done that yet. But this is at 3 cadences. We don't need to do every single cadence because the leg doesn't dictate how fast you walk. It's just the impedance. So just like in a healthy subject, when we walk faster, our joints have higher impedances. So we need to shift the impedance up higher. But this subject can walk at 105 steps per minute with these parameters, or at 80 steps per minute with these parameters. But it feels more natural to him to have the right set of impedances when he walks. So this is a video that shows the walking at these 3 different speeds. And first it'll show regular motion and then slow motion. So a few of the things you can see just biomechanically that this leg does that you wouldn't expect from a typical prosthesis, I'll show in the next one, is you get this knee flexion and plantar flexion at heel strike right here, which is for shock absorption. You get knee flexion during mid-stance, and then you get knee flexion and empowered plantar flexion at push-off. So you can kind of see them qualitatively here. In the next slide, you can see them more quantitatively. So let me explain what's going on here. If you first just look at the center, these 2 plots, this is for healthy subjects. This is the knee angle versus stride, ankle angle versus stride, for 3 different cadences, a slow, a self-selected, and a fast cadence. So this is healthy biomechanics of the knee and ankle joint. This at the top is what you just saw, or this is multiple subjects averaged together. This is one subject, multiple strides averaged together, so that you're not going to expect a perfect match there. But what you can see is this similar behavior between this and this, also for the different speeds, and similar behavior between this and this, also for the different speeds. If you look at the bottom, this is this commercial leg. It's an Autobox C leg with a Freedom Renegade foot. So it's basically state-of-the-art, essentially, as far as a commercial prosthesis. And what you can see is you don't get the same, of course, that knee flexion, as I mentioned. You don't get the right phasing and swing with the different speeds. And the ankle behavior is quite different. And in particular, you're missing this significant amount of plantar flexion, which is dissipative as far as functionally here, and you're missing this plantar flexion, which is for powered push-off here. So essentially, we're able to get significantly improved biomechanics during level walking. The other kind of benefits you get from this prosthesis is at the self-selected speed for this subject increases by about 25%, 24%. We actually have now a second subject that we've tested who also, I think it's like 22 or 23% change here. And we have a third subject consented, but not yet, we don't have a leg for him yet. As far as the, so the caveat, one caveat to everything I'm presenting here as far as the leg is this a single subject at this point, so keep that in mind. As far as metabolic energy consumption, this is shown in overground walking, but these studies, we did metabolic energy consumption experiments on a treadmill at the self-selected speed of the C leg, and we had about 23% greater metabolic energy consumption with this leg, and if we subtracted out the metabolic baseline, then it was even a bigger difference than that. So we're getting some of these nice benefits that we hypothesized several years ago that we could get or would get. But there's other nice things that you can do with a powered leg. And as I mentioned before, level walking, you know, if you look at the preponderance of biomechanics literature, it all has to do with level walking. But, and so granted, probably we do a lot of level walking over nice surfaces in a day, but we also do a lot of other things, and that's really where amputees have, I think, the bigger issues, bigger problems. So one of the things that we do is upslope walking, and so this is one of the things that we've looked at recently. And this is healthy. This is from, I should cite the paper we got this from, but I didn't, and I forget, so I apologize for that. But it's not our paper. But this is the biomechanics of healthy upslope walking at different slopes, right? This is knee angle, ankle angle, and basically what you get is as you would expect, the knee, you have to lift your leg up to go up the slope. So when you heel strike, your knee is flexed, and the steeper the slope, the more it's flexed. And then as you push off here, the knee is essentially almost fully extended because you have this net knee extension because you're going up a slope, you're pushing yourself up. And swing is otherwise essentially the same, but again, heel strike, different place. Ankle, more or less, this is all in swing. So in stance, the ankle is more or less just biased at this slope because you want to keep your body essentially aligned with gravity. So those are the essential ways in which the joints, the leg changes its biomechanics as you go up slope. We can do this with the same, sorry, this is kind of overwhelming maybe, but we can do this with the same controller we had before, but we just changed some parameters. And actually the ones in gray are the ones we have to change. So obviously we have to change a lot of the parameters. And a lot of what's being changed here, right, are like set points, which you would expect. We have to shift the set point as a function of slope. But given that, this is now the data. So I kind of unfortunately switched this up, but this is the healthy subject. This is the same data I just showed before at 3 slopes. This is what the powered prosthesis is doing in the middle. So you can see very similar behaviors here with slope, right? Same with the ankle. You strike the ground with a more flexed knee depending on slope, and your ankle's biased toward the slope as you'd expect. With the C leg and renegade foot, you essentially see no difference as a function of slope. And I'll qualify that because what you can see is a phasing kind of difference. But you don't see any, at heel strike, you don't see any real difference there. So the phasing is a function of how the person's using it, not necessarily the function of the properties of it. So, and at any rate, this looks quite different from that, right? And this looks quite different from that. Maybe an easier way to see that is in this photo sequence. So let's start at the bottom here. This is the C leg. And you can see, or actually we'll start here. The leg is straight here at push off. You can't visually see that there's no powered push off, but there's not. You can see that he's on his toe on his sound side as he swings the leg through because there's not enough flexion, ankle dorsiflexion or knee flexion and swing to get the leg through. And then he has to land with his leg straight because these legs in general, if you land with the knee flexed, then they're not stable and they'll collapse. So he has to land with his leg straight, which is obviously unnatural. Whereas with this leg, you see the knee flexion and push off. Again, you can't visually see push off, but there is a powered push off going on here. He's flat on his sound side. His foot's flat because he doesn't have to worry about the toe scraping. And then when he heel strikes, he's got this knee flex. So this is much more reflective of healthy biomechanics. It's the same thing as the data you just saw, but it's kind of a pictorial version of that. Let's see. Okay, so what we have here, this is kind of, what I showed so far is just walking, but we walked at different speeds, walked in different slopes. So, but what people do is of course, more than that. So we can do things like standing, what I'm doing now. We sit, we go upstairs, downstairs, et cetera. So we need some kind of control structure that can accommodate all of that. So the control structure that we use in the leg is this, and this is just low-level stuff, so you don't have to really worry about that. This is just kind of a controller that tries to get rid of friction and inertia and other things so that we can control the joint impedances better. This is that controller that I showed you before, at least for walking, and then we can estimate the slope using accelerometers on the foot, and we can estimate the cadence. This is a pretty easy thing to do. And as I showed before, take the parameters in here and just vary them as a function of these so we can accommodate walking, upslopes, downslopes, and different speeds. But we also need to recognize when we need to change this controller altogether. And so for that, we have this activity mode recognizer. And for that, we use feedback for this, as I mentioned, but it's instantaneous feedback because it's to create passive functions. But this is actually starting to look at patterns in activity because when I'm walking and then I want to change what I'm going to do, the patterns in all the sensor information will change. So I look at those patterns, and from those patterns, I can train this such that we can recognize when a person wants to change what they're doing. And so this, for instance, inside of that other box I showed before, just this controller, but we have multiple controllers. We have this walking controller, we have a standing, we have a sitting, and now we have a stair climbing and stair descent that I don't have in this, but I'll show some video of that later. So you need to know when to go between those different controllers. And the way we do that is we look at, we take 7 of the sensors on the device, torques and the weight on the ball of the foot, the heel of the foot, and the angles and angular velocities. And we take those and we look at patterns in all of those. And essentially, by patterns, we just take windows, 100 millisecond windows, and we look at the mean and standard deviation of the data within those, and that's 14 pieces of information. And we use what's called LDA, linear discriminant analysis, to reduce that 14 pieces of information to 3 pieces of information, and we normalize it such that everything the prosthesis can do will be a data point. Everything the prosthesis can sense that it's doing will be a data point inside this cube. And then we train it such that when a person's walking or standing or sitting, which is the green, black, and red respectively, these are kind of the clouds. This is what you expect to see while you're walking. This is what you expect to see when you're sitting, and this is what you expect to see when you're standing. One reason why the red kind of stretches from standing to sitting is because that's you transition from sitting to standing. One reason the black and the green kind of interface is because you transition from walking to standing. So we can take these and just model them with shapes, and we choose to use these probabilistic multi-component, they're called Gaussian mixture models, but they're probabilistic models that have one or more series of Gaussian functions to model that data. So one could use lots of different models. But anyway, we do it probabilistically. These respective pieces of data have these respective probability clouds. These, like a Gaussian distribution function, go on forever. But so this is at 5% probability what these clouds look like. So what the system does is at 100 hertz, so 100 times a second, takes this data, checks it against this model, and estimates which activity you're doing. So what you have the highest probability of doing. And if you get that repeated for about 30 samples, then the system says, well, you must want to do this. And then it'll switch to that. And so what that looks like in video is this. We have this video overground, but I like even though this is kind of an old video, I like the treadmill because it's real easy to see that he's changing what he's doing. So that was a transition from standing to walking, where he initiated walking with his prosthetic side. And one of the things, of course, this has to be done without significant without perceptible delay, really, because perceptible delay can be dangerous among other things. So when he goes from sitting to standing, it has to figure it out pretty quickly within a couple hundred milliseconds that, in fact, that's what he wants to do. This is standing. The reason why he's shuffling around is because standing is not just standing still, but doing kind of what I'm doing as I'm presenting, which is, or as you're waiting in a line, which is shifting your weight from one side to the other, maybe turning in place. And then this time he starts walking with his sound side. And so that system seems to do pretty well. One of the things that we have designed in it is it also has to work. Anytime you do intent recognition like this, you're not always going to get it right. And so we have some backups in there, some secondary checks, so that it won't. If it switches into another state, it needs to see something it expects in that state, and if it doesn't see that, it switches back. Because we have about 95% success rate, but you're never going to get 100. But in reality, it has to work for 100. So we do the secondary checks, and we've never had a problem. When it switches, when it gets it wrong, he's never aware of it. Power was something that we didn't know about at first. I mean, one can do pencil and paper calculations, but when you deal with real things, sometimes there's big gaps between that and the real thing. So, and it's hard when you have a person interacting with it as a major part of what you're doing to make the right assumptions, or it can be hard. So we did measurements as far as power consumption. I mentioned the battery we had before. And the other thing I said 120 watt hours, but it's basically the same thing, 118. And what we can get is when we measure average power is that we can do 14,000 steps, which equates to 13 kilometers of walking on a single charge of the battery, which is good. We wanted to be able to do a full day. Actually, for most amputees, this is far more than a full day. And going up 5 degrees, we can get 11,000 steps, and 10 degrees, 9,000 steps. So this is much more than, well, this is more than an active adult would walk in a day. And amputees generally right now, for various reasons, walk a fraction of that, usually about 3,000 to 5,000 steps in a day at the most. So we're well, put it this way, in the next version, we're making the battery smaller because we think the battery's bigger than it needs to be. So that, to me, was, I guess, a nice surprise, and is reflective of the fact that, as I mentioned, that the battery technology has gotten considerably better in the last decade, really, in large part probably driven by the automotive market. But we get to reap the benefits of those advancements. I mentioned before that we're working on stair ascent and descent. So this is stair descent. This is the IRB mandated helmet.
What did he do at the very beginning? It looked like there was some switching.
Yes, there was. Yeah, I was going to mention that, but but you did. So I didn't know if somebody would, if that'd be something to mention. Let's see. We are experimenting with different ways to do this. So this pattern recognition that I mentioned, ideally you'd like somebody to do what they're naturally going to do, and it would pick it up. But we believe that might be too dangerous for doing things like going downstairs. So we need a person to, the way we're doing it right now is it's still the recognition, but we want the person to give it a clear cue. It's not a cue like, doing a strange dance, but something that they might do, but again, to make it easier and more clear for the pattern recognition system, and really for issues of safety, because you need to do the right thing when you go downstairs, or it can be real dangerous. So that was an early way we actually have, and that required something like a half a second of delay. And now, and this is video that was taken, and something we implemented probably within the last 2 weeks. We've improved that, so there's essentially no delay.
What did he do?
Oh, but what did he do? He held his leg out like this, and then the cue to him that the leg switched modes is that the ankle started to dorsiflex. That means to him it went into stair descent mode.
So you just he lifts it up, and the ankle.
It's like he's going to go over the stairs, but he doesn't. But he freezes there for a little bit. He freezes. It says, okay, well, clearly he's not doing something that he's not doing regular walking, and so then it says, okay, I'm going to dorsiflex my foot. When he dorsiflexes the foot, that says to him, okay, it's in stair descent mode, and he can start going. That's non-optimal. We're better now, but that's the way we were doing it then. That was taken from the summertime.
Just show the beginning of that again.
Okay. All right, but if I run over time, it's not my fault. the beginning of that, yes, okay. Okay, and there's another question?
Yes, have you thought about augmenting your sensor data with EMG and sound lag to increase your...
Kind of, a hybrid of that. So augmenting it from the prosthetics leg with EMG. We don't want to put anything on the sound side. I mean, right now, when a person, the state of the art is that people wake up, they slide their prosthesis on, and they go. So we really are hesitant to do any instrumentation of the sound side. That OSER leg that I showed you before, they had sound side instrumentation, and they had wireless Bluetooth communication between the two, and we just don't want to do that. And I don't think you need to do that. But we are working, and I know that you had done some work at RIC, it's my understanding, we're working with, there's a TATRIC contract. This is primarily funded by NIH. However, there's a TATRIC contract that we work with, and we work with guys at RIC. They're looking at combining EMG from the prosthetic side to supplement that for issues of pattern recognition and other things for control, to see if you can do, obviously you start to get some more intent information if you can tap into the EMG. Okay, so I want to kind of keep track of my time. I forgot to bring my watch, so I don't want to spend too much time on this, but I'll go quickly. One of the things that I think, I mentioned this falling, and there's some studies out, some really good studies actually by Miller on 450 roughly amputees, a lot of data talking about falling and fear and falling in amputees. There are several reasons why amputees fall, and not having a healthy set of biomechanics is one reason, as I mentioned that in that slope ascent and stair descent and all that. But another reason is that if they start to fall, they don't have the recovery mechanisms. And so one of the things you can do with the power prosthesis is you can start to provide recovery mechanisms, both in balance. So if you're in a subway train and the train suddenly stops, right, we have reflexes to deal with that. We can put those into prostheses. And then also if we're walking along and texting on our phones and stumble, we have reflexes to help recover. And so we're starting to look at that. And this is a video that we took. This is healthy subjects. And only to explain that there are two basic, at least for stumble now, there are two recovery mechanisms, essentially two. One is elevating, where your foot, this is a obstacle that comes out and locks, right? You pull your foot, elevating is you pull your foot up over, you extend it out, and you arrest your forward momentum as biomechanicists like to describe that. The other is lowering. What was that? No helmet required. Not sure actually what to say there. I guess I'll say this. Yeah, since this is being taped, I'm just not gonna incriminate myself. This is the lowering, where you just decide not to pull this foot over, but actually you're late enough in swing, you lower that, you pull the other foot over. So we've started to implement these behaviors in the prosthesis, and here you see we have the harness. This was an elevating response. You can see it hits the obstacle, the leg gets pulled over it. And these are fundamentally active responses. You can't do this with a power prosthesis. And that's been recognized in people who do the in healthy subjects for the biomechanics folks who do the inverse dynamics and look at joint power and torques. That elevating is fundamentally powered. That's lowering. Just to show that we have enough sensors, we have enough computation to figure out what a person's going to do, and then you have, importantly, the actuators here to actually implement it.
Does he know which one of these is going to have?
He does in this case. Obviously, that's not. So these are preliminary. We haven't started an official study of this. Okay, so that's where we are at with the leg, and I mentioned I wanted to use some of my time to talk about the arm stuff as well. So, and as I started with the leg, by the way, I'll come back and just kind of say what we're doing with the leg at the end of the talk. But But I want to talk about commercial state-of-the-art in hand prostheses, and you basically have body-powered and you have myoelectric, and both, I think, remain state-of-the-art. Both, and I think pretty much everybody here understands how these work, but just briefly in case you don't, in the case of a transradial amputee, you're going to put a myoelectric, a surface electrode on the dorsal aspect and ventral aspect of the forearm respectively, and use the EMG signal from dorsal to open one of these and from ventral to close one of these. These look like they have multiple fingers, but they don't. They're really, they're all pinchers. So one of the things I can easily summarize this slide basically by saying that in both cases, these are single degree of freedom devices. And I mentioned the improvements in robotics technology, relatively recent improvements. In the case of the leg, of course, that has enabled powered prostheses. In the case of the hand, it enables a higher degree of freedom hands that have considerably more dexterity than that single degree of freedom. Obviously, in activities of daily living, we do a lot more than just this. And so, because of that, you've had these recent descriptions. I think the Smart Hand by the SSSA group in Italy has done a good job of developing a hand. There have also been several recent, this is a rapidly changing commercial landscape, but there are these what I'll call emerging devices. I have pictures of them on the next page who are leveraging these advances in robotics. This is the Autobox Michelangelo hand. This is actually a 2 degree of freedom hand, so it has multiple fingers, but it has two grasps, a lateral and a pinching. So basically the thumb has two positions. So it's a 2 degree of freedom hand. This is the iLemb. It has a motor in each finger, but the abduction, the thumb opposition or adduction is manual, so you take your one hand and move it over. This is Deca's arm, and then this is the Biomedical hand, which is similar in this as far as to this as far as the powered versus passive degrees of freedom. This is the hand or a prototype of the hand that we've developed. So of course we're and ours of course is better than everybody else's. Some of the ways in which ours is different in any case is we use additive manufacturing. Formerly called rapid prototyping, but now getting good enough so you can do things that you can't do with traditional machining. We have series elasticity in here, which does various things as far as, among other things, gives us an ability to do force control from what is kind of inherently a motion control system. So we can do both motion and force control. We do some interesting things, I think, as far as sensing for force and motion. And then we use brushless motors, which increase the power density. All of these hands, the previous ones I showed, are a little bit weak. And brushless motors give you the ability to increase the power density by a factor of 3 to 5. But in order to use those in a realistic device, you have to have the appropriately scaled microelectronics or brushless servo amps to drive them. These don't exist right now, but we have spent some time. Basically, we have a set of, we've been developing those, and we have a set that should be done within roughly 6 months that look like they're going to be appropriate and effective and so on. The distribution of actuation, well, so here's the actuators sit in the hand. So here's 4 what we call motor units. And I'll just show you, this is kind of a glass stand. This doesn't really exist. That's a solid model. But you can see this is also a solid model. If you remove the palm structure, you can see these motor units. You can see they have pulleys. These tendons come out of the pulleys and are routed up to each hand. So the way it works is we have 4 actuators, and one actuator does index finger flexion. Another actuator does these 3 flexion together, although they're differentially coupled. And then the thumb has 2. The thumb has a flexion and then an opposition. Yes, okay. And each motor unit looks like this. So it's a 12 millimeter brushless motor. And here's where the tendons rolled up on this thing. This is called a 2-way clutch, which we designed. And what it is a way to, the way we use our hands a lot is when we grasp something, we use a lot of effort to grasp, and then we usually, let's say I'm carrying a briefcase across campus, I'm going to grab something and hold it there for 30 minutes as I walk across campus, and I don't want to have to use power the whole time I do that. So what I want is a non-back drivable system. I want, and you can do that in a few ways. There are ways you can design in non-back drivability by using friction, like in a worm gear. But the problem is those are lossy. Those are worse in the backward path than in the forward path, but they're even lossy in the forward path, and you don't have that much power budget to just throw it away. So what a two-way clutch does is enable you to easily drive in the forward motion and not, with high efficiency, and not back drive in the backward motion. So that's what this does. And of course, the key to doing it here is doing it in a real compact way, in a way that can sustain a lot of force. So at any rate, each motor unit has that. So we can grab something, turn off the power, and hold it for a long time. And then we just have to use power when we change the configuration of the hand, not to maintain a configuration of the hand. Each finger has this, in the tip, has a series of elastic elements. So here's a tendon. It snakes through. Actually, this happens to be the thumb, but it's a similar configuration. So that series of elasticity does a few things, but it allows us to do force control. I mentioned that non-back drivability of the clutches, but what non-back drivability means is that you can only do motion control in general. But if you have a series elastic, which basically maps motion to force, then we're doing motion control when the hand or the fingers are free. Once we grasp something, then that motion control becomes force control because of this. So we can do both and still have that non-back drivability. So I told you about locking in position. Well, alternatively, if I grab something and squeeze it, and then turn off the power, then I lock in a force instead of locking in a position because of that series elastic element. It also has some other nice things, like for shock loading and whatnot. But we have these parallel elastic elements, which are torsional springs in the joints. That does a few things, but one is we're under actuated, and so that makes it a deterministic system so that we can determine the sequence in which joints will, joints will move when we actuate it. And then it also provides, right now we just have a powered flexion, so the extension, finger extension is passive. And then this additive manufacturing enables us to do things like make curved tendon paths to decrease friction and make hollow links to decrease mass. The hand was designed to do 8 different grasps, and these are 8 grasps that we believe, and that also if you look at some of the grasping literature, that cover the majority of activities of daily living, let's say 80%, although you can't really put a percentage on it. But if you can do these 8 grasps, you can do a lot of things in activities of daily living. This is a video that shows some of that hand working. I think it kind of got stretched out here, so the aspect ratio isn't really right, but you get the idea. Right now we have off-board electronics, so these are just the wires going to the brushless motors. This is some indication of the under actuation, which gives it the ability to, of course, wrap around things. Those are the thumb degrees of freedom, finger degrees of freedom. Of course, like I said, you have to move all these together, although they are on a differential, so if you hold one back, the others will flex. This is just showing that some people, I guess it's just showing from different angles and kind of making clear that all the actuation is in the palm. For whatever reason, when I show that, some people don't seem to, it doesn't come across sometimes. And I'm going to check my time. Okay. Yeah, that's the obligatory handshake. Okay, so I mentioned with the leg that, you know, making the device is one important part of it. You have to have a device that works effectively and has the biomechanical levels of force and speed and is within the right geometric envelope and is as light as possible. But, you know, once you have all these degrees of freedom, control becomes a real big issue. Because one of the things about these is a single degree of freedom, but they're easy to control. They're easy and intuitive. And just because you have more degrees of freedom, if you have those degrees of freedom, but it takes real cognitive effort, we'll put it this way, if they're very difficult to access, functionally access those, people aren't going to use them. It's just like the old VCR remotes with 1,000 buttons on them, and you know, who cares if you have these functions, you're not going to use them. So this is something, there is some trade-off between functionality and cognitive effort. And this has clearly, you know, has demonstrated that people, it's something that people are willing to use. It's robust. You don't, well, actually, I was going to say you don't drop things. That's not true. Some people do drop things. So, but it's fairly robust, and you get proportional control and so on. You need a system that enables you to access this functionality in an easy way. And it's something that needs to provide intuitive, real-time, robust, reliable, and proportional control. You could argue about proportional, but I think it needs to be proportional. So there is a lot of interesting work going on here. I kind of did this generic. This is all very qualitative, so these lines, the position and space doesn't mean that much. But you generally have more invasive, less invasive ways to do things. You have cortical implants. You have peripheral implants. This is the targeted reinnervation, which is EMG, but increasing the number of EMG channels. And this is kind of more traditional, just going with the EMG that you have. It seems to me that there is this general, of course, trade-off between invasiveness and potential for full neural integration. Sensory feedback is a big deal. With this, it's unlikely you're ever going to get much sensory feedback. With this, maybe some, but also unlikely. And then you start to get more, and if you can do the sensory, if you can get into other cortexes of the brain, other parts of the cortex of the brain, then you can possibly do more. What we do, and I don't have time to go into the structure, but we're using a surface EMG approach. I think one of the, well, I don't know if I should give my own opinion. I think people should continue to pursue the neural interfaces. I think there's a lot of potential there. But in the interim, what we're using is a surface EMG approach because we don't want to have, we don't want our hand to sit in a research lab just because we're not, there's not a way to do full neural integration at this point. So what we have done is use surface EMG and together with a lot of sensory information here to give the hand a lot of low-level intelligence so that the user thinks about high-level things. The hand feels essentially what it's grasping in some regards and does the low level. Similar to what we do with our own hand because we don't think joint by joint. We think, you know, generally here's the shape of something, I want to grab it, that's what I'm going to do. Or it's a little bit more complicated with gestures. But I'll just show you, we have a method that seems to be effective with regard to EMG. It's a two-channel EMG approach. So here's one channel, here's another channel. So it's modeled, I mean, it uses the same kind of electrode configuration that would be used in a single grasp prosthesis. But there's a whole underlying structure and this is, by the way, this is a doctoral student. This brace is on the arm because it's supposed to be a better representation of the muscle structure in an amputee. And this shows the various grasps. And some of what he does here, this, I have the word bimanual task because this is him handing himself things. So I think we didn't do that intentionally, but it seems to be a good indicator that there's not serious cognitive effort involved if he can hand himself things. Let's see. Yeah, this is more tip grasps. And, okay, and the obligatory handshake.
Why did you choose to put them in opposition?
Put what in opposition?
Instead of parallel.
Oh,
Why did you choose to do that?
lack of forethought. And there's no reason why we chose that. We just videoed it. Another thing that we're developing, because we're going to start testing this on amputees, is this we call it virtual prosthesis. So it's the same thing, but the difference is we can actually give, this blue is kind of a desired pose. So we can have the same EMG interface, but give a desired pose and measure the time to acquire different poses and compare that to well, use that to benchmark our own controller and compare it to healthy subjects. And so this is just a brief video, and then I'm getting toward the end of my time. Yeah, so I have, I think, one more slide after this. This actually, maybe I can wait and show this. Okay, well, this is the only part of it actually I wanted to show that's different because we didn't show in that other video kind of continuous control. So you can do one thing, some people use pattern recognition. One problem with pattern recognition sometimes is it just goes to a certain grasp. This actually you can use for full proportional control between grasps. We didn't show that in the hardware just because we didn't think about. We also in the hardware didn't show gestures like this. We were just showing grasps. So this as opposed to grasps is showing gestures. It's the same control system though.
So is he engaging in particular behaviors in order to access each of the different types of grip?
Yes, I will. So if I could just, oh, this is the target acquisition thing. since I don't, can I address that in a question just so I can actually say that I finished my talk in time? This is a cosmesis, which is a very important part, and we're working on this. It's a hard thing to do, but it's an important part. You can't do real activities of daily living without that. And then this is my penultimate slide, which is what we're doing with the knee right now is we want to do those biomechanical characterizations on 3 subjects. I just showed it on 1, and right now we've done 1.5, so we need to do the others. As I said, we're starting to work more on the balance and stumble recovery, and we're also implementing some next generation hardware just to do improvements and actually make it a little bit audibly quieter, because it's not as audibly quiet. People would ideally like silent devices. It's not, we're not going to get there, but our next version is supposed to get closer. And then what we'd like to do is that virtual prosthesis study on 5 healthy subjects. Actually, this is what we're doing now, today. The student was doing the night I left, or the night before I came here, I was a subject for that. We're also doing some next generation hardware with an integrated cosmesis, and then we want to do that study on 5 transradial. We want to compare to a standard myoelectric hand using the Southampton assessment procedure. So just the last slide is these are the people in the lab who deserve credit for this. I just sit in my office and edit papers. Let's see, this is Don Truex and Brian Lawson and Adicon Vero and Skylar Dally. This is Daniel Bennett. He was a student here who is working on hand design. But he got his undergraduate and master's degree here at Case Western. And this is Tuma Swiss. And these other guys are students in the lab working on other projects. But anyway, that's the end of my talk. I appreciate your time. I appreciate the opportunity to come and talk.
Right on time. So before we open up to questions, I just want to give Michael a token of our appreciation from the FES and APT centers. And that's for you too.
Okay, thank you. Are these my very own electrodes I can plant for myself?
Yeah, well, you can do anything you want to yourself without IRB approval.
Okay.
Or a helmet. For those of you wanting to ask questions, I ask you to speak up or gesture to Kathy Walker. She has a microphone. Remember, we're being webcast, so the people at home need to hear you too. And those of you watching on the web, if you email your questions, we'll try to get to them before the end of the session. Okay, so where was that outstanding question? Oh.
I was just curious about it. Are those behavioral, I almost want to call them behavioral icons? Is he engaging in particular behaviors in order to initiate each individual type of grasp?
Yeah. What he's doing there is there's a map. And all of those graphs are represented in the map. And he chooses, he branches, let's see, the things that he's doing, he co-contracts the muscles in order to switch from one map to the other. There's 2 maps. Just like I mentioned for the foot, when the foot goes down, the person knows they're in stair descent mode. This happens by when he switches maps, the thumb position changes. And the thumb position basically then says what sequence of postures you're going to go through as you flex and extend. The person doesn't have to worry about changing the sequence of postures. If I want to go, so the sequence of postures is done. There is a certain sequence if there's no object in the hand that will be followed to acquire certain postures. And if there is something in the hand has motion sensing and force sensing. And it decides, based on what it's contacting and which map it's in, how it switches from posture to posture. So there's 4 actuators in there. And a person never thinks about which of the 4 they're doing. They just flex and extend. And the system knows enough about its own configuration to then switch the coordination of how it's controlling each of the motors. That's not a great, what I really need is a diagram. But I know putting up that diagram, I could do one of 2 things: put it up too quickly for anybody to understand it, or spend too long and on it, if you know what I mean. So that's why I chose not to put it. But so there's a certain level, low-level intelligence, and there is a simple map. That's the thing about, if you have a complex map, then it takes too much cognitive effort. If it's simple, then the idea is that as you grab for something, you know essentially which map you want to be in. You can do that twitch really essentially before you grab. Once you grab for it, then it's just a matter of either flexing your the muscles on the ventral or dorsal aspect of the forearm and just close and release, basically.
So you set the path and it makes the decisions from there. So
yeah, and the person's really just giving it to proportional, either giving it a general command in one direction or another, if that makes sense. Sorry, that's not a wonderful explanation, but I think it would really take more time, and I don't have I could fish for a diagram. I don't have one in this presentation. Yes?
I know you've done some great work in orthotics, but I saw
thanks.
nothing in your talk, so I was wondering, are you out of orthotics business?
No. We're doing orthotics work, and so these other guys, Ryan, Ugo, Spencer, Kevin, are working on orthotics things. And I think there are a few things about that. One is we don't have as much experimental results in that regard as we do in the others. So, and Kathy, being the very punctual person she was, asked me, I think this summer, for my presentation title. And I didn't want to commit to doing presenting work on the orthotics when we didn't yet at that time have much experimentally. I have a little bit more now, but also part of it was just not wanting to talk about too much. But so I know I'm meeting with you later. I'd be happy to talk more about some of the orthotics work. I'm still pursuing that, yes. Yes?
Are your impedance parameter subject specific or global?
Good question. We hope they're global, and we don't have enough subjects to know. But we do have 2.5 subjects, and it appears that they don't vary much from subject to subject. So what ideally we'd like is for those to be, let's say, a function of weight. They might be a function of height and weight. And so because it's completely unrealistic to have a large set of parameters you're going to tune for everybody, I think. So we just need to include some more subjects before we know that. At this point, when I say 2.5 subjects, we have the 2, and then another subject we kind of false started with, and so he walked on it for a couple days. And he could walk, put it this way, a subject who's physically in size and weight pretty different from the other subjects we have can walk on the prosthesis with we took the set of parameters from the one subject, and the other subject, who is notably different, could walk on that set of parameters first time, right away. Now, it's not the optimal set for him, but so we're hoping it'll be a function of size and weight, but with 2 data points, we can't make that fit right now. Yes?
Can you tailor the actual geometry of this prosthetic, like of that limb, to people of different body, like if they're taller or shorter?
Yeah, you're talking about the leg, I guess.
Yeah.
Yes, there's certainly adjustability, and we use the same actuators, the same battery, but there's length adjustability both in the foot and the shank. So, yes.
What would be changed for a bilateral loading?
I would hope that nothing would be changed, but we don't know that until we would try it on somebody. But it's designed only to rely on the information from its own side. That was one of the things about, I told you the decision not to have any instrumentation on the contralateral leg. There were 2 reasons for that. One is I don't think people want to deal with it. The amputees, they don't want to have to strap on all this stuff before they go out for the day. The other is that it does rule out, it doesn't necessarily rule out, but it makes it much less likely that it's going to be effective on a bilateral. So this, we believe, there's nothing that we've done that would obviate the fact that it should work the same way for bilateral as for unilateral. Because it's really getting all its information, well, not, the majority of its information is getting from the ipsilateral hip. I hesitate because the rest of the body, what the rest of the body is doing also affects it, but for the most part, we're taking information from the ipsilateral hip, and both hips are intact. Our approach, you didn't ask this, but would be much less suited to a hip disarticulation. But that's a hard problem for other reasons as well. Yes?
Thinking ahead to implementing your hand in an individual who has either a short transradial amputation or a transhumeral amputation, are you guys thinking about adding supination and pronation for those individuals?
Yes. So we would like to add wrist, and of the wrist, it seems that supination, pronation, or wrist rotation, whatever you want to call it, is the most critical. So we want to add powered wrist and an elbow for a transhumeral. So we're kind of building things up in a modular sense. So I guess I'll put it this way. We expect to start developing the wrist probably within a year. So it's in immediate plans, but we did choose to start, most distally and build things up in a modular sense, just because that made sense to us for various reasons. Also, if you look at the control issue, of course, going from very few degrees of freedom to a lot, then the hand is where the most of those issues reside. But yes, we plan to do that.
All right, one last question.
Yes.
How would the knee respond to the subject carrying a briefcase?
Excuse me?
Say it again.
How would the knee respond to the subject carrying a briefcase?
How would the what respond?
The knee.
Oh, the knee respond. Oh, yeah. Good question. It seems to do fine. So that's a real good question. And so we have, and I have some other video that shows, I don't remember, a pretty heavy 8-kilogram briefcase. And then also we have, I don't know, 10 to 12-kilogram backpack. And so that was a concern. We tested that because of the pattern recognition stuff. Is it going to mess that up? And so, yeah, we have a video. Actually, we didn't think of that ourselves. We submitted a paper, and the reviewer said, you need to do that. So we did that. But it seemed to, it worked fine. And so, yeah, we have a video of him, and he's got both on, and he puts down the briefcase and walks on, and then takes off the backpack and walks on and picks up the briefcase, and seems to do fine. So those patterns seem to be sufficiently robust to variations like that.
I guess now you know who one of the reviewers was.
Yeah.
All right, I'd like to thank our speakers.